Okay, thank you. So I'm going to talk about this paper with Jivan Chandra, Scott Collier, and Alex Maloney on semi-classical 3D gravity from averaging large CCFT. So I'm going to start with a few words of motivation. Motivation comes largely from this recent work on two-dimensional gravity. So we know now that 2D gravity is holographically dual to random matrix theory. And this seems to be fundamentally different from the earlier string theory examples of ADS-CFT, because the boundary theory is not quantum mechanics. Okay, random matrix theory is not quantum mechanics. For example, observables in two copies of the boundary theory don't factorize. In quantum mechanics, the partition function is a number. And if you calculate the product of z of beta 1 and z of beta 2, you get the product of two numbers. They're completely uncorrelated, just completely obviously in quantum mechanics. But in random matrix theory, they're correlated by the disorder, by the integral over random matrices. And that's realized in the bulk by connected topologies in the gravitational saddle. So this picture here and all the pictures that I'll draw in this talk is a space-time wormhole, a Euclidean wormhole. The boundaries here are, in this case, two quantum systems. So this boundary circle is the thermal circle of one quantum system. This is the full thermal circle of the other 0+1 quantum mechanics. And the shaded region is the bulk topology that connects them. Now that's two dimensions, but there are many reasons to suspect that averaging or coarse graining of some kind must play a role in higher dimensional gravity as well. For example, there are space-time wormhole saddles studied by various people, but in particular, there's a paper of Maldacena and Maus, where they constructed these saddles, and still we have these saddles and no known instabilities. So their role in ADS-CFT is still unknown. Now, I want to emphasize that I am not saying that UV complete quantum gravity is some kind of ensemble average. I'm just saying that there are some solutions of gravity which don't factorize, and we need to understand their origin. So we should try to figure out what they mean from a CFT point of view. These solutions exist, and if anything, this factorization puzzle is even more puzzling in higher dimensions than in two dimensions, because in higher dimensions, these are solutions. These are on shell. These seem to be perfectly well-controlled contributions to the path integral, and we have to figure out what they mean. Okay, so the question we're asking is, what is the CFT interpretation of non-factorizing bulk solutions? The proposed answer, so we proposed an answer for 3D gravity, and the proposal is that these come from an ensemble average over approximate solutions to the Bootstrap equations of a two-dimensional CFT. I'll explain what I mean by that. So there are, so is a precise proposal. There are two calculations that need to be done, and I'll go through both of them in this talk. There's a gravity calculation, which is finding these wormholes and calculating their contribution on the gravity side. There's a bunch of wormholes on this slide, which are among the ones that I'm going to talk about. There are lots of different kinds of wormholes that we can consider. These are all solutions of 3D gravity. I'll explain what the pictures mean. So there's a gravity calculation, and there's a CFT calculation where we have to define what it means to do this ensemble average and calculate the average. And we're going to do both of those calculations and see that they agree with each other. A couple words before we get started. One is what bulk theory are we talking about? So we're talking about a theory that's Einstein gravity in 3 dimensions plus some massive particles. Now, we could add quantum fields, but that's going to really complicate things. So the only thing I'm going to consider here is massive particles in the bulk that contribute with a world line action. The solutions of this bulk theory in 3 dimensions are in principle known. They're just quotients of hyperbolic space. The fact that there are massive particles means that they don't have to be smooth quotients. They can have orbifold singularities corresponding to where these particles are inserted, but they're all just going to be orbifold quotients of three-dimensional hyperbolic space. Another thing before we get going is a natural question at this point is, what does it all mean in a fixed theory? Why are we talking about ensemble averages if we're interested in individual CFTs? I don't know the precise answer to this question. I won't try to answer it in this talk. I can speculate, though, that I think that this is some kind of coarse-grained description of what's available to an infrared observer. I think it's an important problem to understand exactly what that means in a fixed theory. What kind of coarse graining am I talking about here? But I'm not going to get into that in this work. We're just going to define an average and do the average and see that it reproduces gravity. I'll start on the CFT side. So we need to define what it means to average over CFTs. The goal is to define an averaging procedure that has a large central charge, a sparse low energy spectrum, and approximate crossing invariance. The large central charge is the fact that we want a semi-classical theory in the bulk. The sparse low energy spectrum is the fact that we're not including, well, we have a limited amount of particle content in the bulk, so it's a gravity-like theory, not a stringy-like theory. And obviously we want it to have some kind of crossing invariance as well. Okay, so to define this average, we're going to average over matrix elements of primary operators, in other words, over OPE coefficients. And that means that we're not really doing an average over an ensemble of true CFTs. So this is not an average over, well, there have been other discussions of averaging in CFT that have been averaging over moduli spaces or conformal manifolds, where everything in the ensemble is an exact CFT. This is not like that. These are not true CFTs. Similarly, in random matrix theory, we imagine in random matrix theory that the matrix we're averaging over is the Hamiltonian of some quantum system. And each entry in that ensemble is a potential quantum mechanics. Now, so it's different from that. We're averaging over this approximate CFT data. And I think most draws from this ensemble that I'll define are not true CFTs. They sort of lie in the swampland. This is similar to the eigenstate thermalization hypothesis, where you average over matrix elements, or you treat your matrix elements as random variables. ETH has previously been applied to JT gravity plus matter, especially starting in this paper of Phil Saad that talked about the information paradox in this way. So the way that I'll be doing averaging is not very much like the random matrix of the SSS duality, JT gravity, but it is similar to what's been done, similar in spirit to what's been done in applying ETH to JT gravity plus matter. ETH and a similar averaging over OP coefficients has also been discussed in higher dimensions. And in these papers, they've seen some qualitative similarities to gravity and done various CFT calculations to support this. But there isn't really a detailed comparison to the gravity side, and that's something that we're going to do. So there's a crucial difference in higher dimensions in doing averaging in general over quantum field theories in higher dimensions. And that's that you have to account for locality in the boundary directions. In other words, you have to account for the bootstrap constraints. You can't just do any old average over these observables. You need to somehow account for the bootstrap in doing that averaging. Another comparison I can draw is to this this famous paper of these authors on solving the bootstrap equations order by order in 1 over n. Okay, so we know that solutions of the crossing equations order by order correspond to bulk effective theories, but you could ask, how do we include black holes in this story? There was a more recent paper that did something similar at finite temperature, also order by order in 1/n. But I really mean something different here, which is including black holes, including black hole microstates. And the fact that there are non-factorizing contributions on the gravity side, I think means that something has to really change when you include black hole microstates in this story, because from the gravity point of view, it should not satisfy the ordinary axioms of conformal field theory in order to reproduce things like these non-factorizing saddles. You really have to do something different once you include the black hole microstates. Not if you were doing it exactly. Presumably, you have a single UV complete theory. But if you want to do it, if you want to study the effective theory that corresponds to gravity in the bulk. So I'm now going to explain how we define this average. The starting point for the spectrum. So we need to define the CFT data. That is the spectrum and OP coefficients of the CFT. For the spectrum, we're going to use the Cardi formula. The Cardi formula tells you the density of states in terms of H and H bar. And you can think of this formula, so rho 0 here is the Cardi formula. And you can think of rho 0 as the crossing kernel for the torus identity block. That is, you take the identity in one channel on the torus, you transform to the other channel, and from that you read off a density of states. That's the Cardi density of states written here. There's a similar universal formula for the OP coefficients of a 2D CFT. Okay, so this was discovered more recently. What it tells you is it gives you a formula like this. On the left-hand side are the OP coefficients of individual primaries. So IJK labeled primaries in the Virasoro primaries. And what it tells you is that if you average over some window, and you're in a fixed theory and you average over some window of primaries, then that has the universal behavior, which is given by this function, by this universal function C0. Okay, so rho 0 is the universal function for the spectrum. C0 is the universal function for the OP coefficients, and it's a smooth function of the weights. So this is just a function, a smooth function of the weights, whereas the left-hand side is some thing that depends on individual states. The defining feature of C0 is that it's the crossing kernel for the identity block in the sphere 4-point function. It satisfies this crossing equation for the block. So you take the identity block with operators equal in pairs, you transform to the dual channel and expand in Virasoro blocks. That defines C0. And in these papers, they calculated C0. And a nice thing that happens is that you can express it in terms of the Liouville structure constants. That's this formula here. So on the right-hand side, this is the DOZZ formula. Liouville is completely solved. The structure constants are known. So there's this is the DOZZ structure constant. And C0 is related to that by some factors of the density of states. Now, to avoid confusion here, it's not that there's actually a Liouville CFT here. The reason that Liouville is showing up is because there's a relationship between representations of the Virasoro algebra and Liouville theory. And so it's sort of showing up, it's just playing an auxiliary role because of its relationship to the Virasoro algebra. It's not that there's an actual Liouville theory. And in particular, the arguments here don't even mean the same thing. So as they would in Liouville. Like in this formula for C0, these H's are the chiral weights, the left moving weights of some operator with spin. And that's what they mean here. Whereas Liouville theory doesn't even have operators with spin. Okay, so it's playing a different role, but it's the same function. So now I can define the large C ensemble. These formulas are universal. They're true at high energies in any CFT, but motivated by the gravity side, we're going to assume that they're true all the way down to the black hole threshold. That is, we assume the Cardi spectrum for all states above the black hole threshold. The lightest black hole in 3D gravity has weights c/24. So we assume that the theory obeys the Cardi formula starting right at c/24. You can think of this as well, you can almost derive this from the bootstrap just by assuming large central charge and a large gap. There's some ambiguity right near in the region near the threshold. So that's not, you can't quite derive it, but we're going to assume that this is true all the way down to the threshold. In addition to this Cardi spectrum of black hole states, we'll also, if you want, you can also include a discrete set of primaries below the black hole threshold. Now, I'm going to assume for the purposes of this talk that those are relatively heavy. So the upper bound in this range is the black hole threshold. The lower bound is here to ensure that there are no multi-particle states. So if I take my particles to be above c/32, then 2 of these particles makes a black hole, not a 2-particle state. If I include stuff below c/32, then we have to worry about all the multi-particle states and Virasoro mean field theory. I think we could do that, but it would really complicate the story, and I'm going to assume, for our purposes, that we don't include anything below c/32. Okay, so that's the spectrum. Now I need to tell you the OPE coefficients. We assume that this universal OPE function holds on average for all primaries other than the vacuum state. Okay, so we are going to treat the OPE coefficients as random variables with 0 mean. Their sign is oscillating, but with variance given by this universal formula. So what I'm doing in this equation, I'm defining the bar. Okay, so I'm defining that defines what we mean by average. The average of a single OPE coefficient is 0. The average, when you square them, has this variance, and we treat them as independent random variables. The higher moments are calculated by Wick contractions. So we're assuming that that these are Gaussian random variables. There are corrections to that, which I'll come back to in a moment. Okay, so that's it. That defines the large C ensemble. To recap, it has a Cardi spectrum plus some subthreshold point particles will correspond to these point particles. They're point particle operators, which will correspond to whatever point particles we include in the bulk. And OPE coefficients with 0 mean and statistics set in this way by the identity block and this universal function C0. Then the conjecture is that all classical solutions of 3D gravity plus massive point particles match to CFT calculations in this ensemble that I've just defined. The conjecture includes loops. We've checked some one loop corrections. A few comments. First of all, this ensemble that I've defined is crossing symmetric on average. It's been designed that way. So like the 4-point functions are, it was designed so that the 4-point functions are crossing symmetric, and the torus partition function is crossing symmetric. In fact, once you put that in and assume this Gaussian statistics, you get much more than that. It's also, there are also higher point functions are crossing symmetric. Well, many of them are. And higher genus partition functions are crossing symmetric on average. There are some caveats to this. First of all, that it's only true on the first sheet. This is, so like, there are branch cuts in the correlators that are not being accounted for here. One way to think of this is that the spectrum that I've defined does not have integer spins. I gave a continuum. I said that there's a continuum in H and H bar, which means that H minus H bar, the spin, is not being restricted to integers. Okay, so that introduces branch cuts. You have to stay on the first sheet for these calculations to make sense. I think we would like to understand how to correct that. I think it's something you should be able to correct order by order and compare to the bulk, but we haven't done that. The second caveat is that they're non-Gaussianities, which I'm about to come back to. Another comment, I said nothing about energy level statistics. There's been a lot of discussion of energy level statistics in the JT duality in random matrix theory. They're connected to the spectral form factor, which is basically the picture I had in my first slide, the wormhole with two circles at the ends. That's related to energy level statistics. But I don't have to say anything about them for our purposes, and that's because we're talking about classical solutions in the bulk. It appears, based on all the examples that we know of, that classical saddles don't care about the energy level statistics. That, at least in Euclidean, perhaps at late times or something, they do. But this discussion in JT, those were off-shell gravity calculations. They weren't classical solutions. We're talking about classical solutions, and it seems that in this case, all we need to the classical solutions encode the statistics of OP coefficients, whereas these off-shell calculations are related to energy level statistics. Last comment here is that this definition of the ensemble is not exact. It should be viewed as the leading order data used to solve crossing iteratively. We've done that in some examples, like iterated to next order in some examples, and I'll explain one of them. But we don't have a systematic way to solve crossing order by order here. You can at least perhaps roughly compare this to the spectral curve in random matrix theory, which is just the input at genus 0, which you then use to solve for the theory order by order. Now, I mentioned that we're treating it as Gaussian, but there are corrections to that. So what are these corrections? Well, there must be non-Gaussian corrections. This follows from looking at 4-point functions. It follows from the structure of the crossing equations. These corrections presumably come with e to the minus s suppression factors. That's necessary for this whole story to come together, to fit together. And comes from estimating their contribution to correlation functions. In the bulk, these would be suppressed by the fact that they come from higher topologies. But we have to be careful because what I mean by suppressed is that they're suppressed if you write down the statistics of the 4-point. Say you want the statistics of 4 OB coefficients, then the first term here is like a Wick contraction. The second term is a connected term, so that's a non-Gaussianity, and it comes with an e to the minus s size coefficient. However, there are more, like if I gave the delta, so there's like a delta ij, delta kl, delta mn here, and these connected terms have fewer deltas, so they can actually contribute to depending what you calculate with these OP coefficients, they can potentially contribute at leading order. Okay, so there are some observables where these non-Gaussian corrections are the leading contribution, even though they're e to the minus s suppressed. We've not studied these terms. I won't have much to say about them, but I just wanted to explain what we need their structure to look like. In order to really extend this to all orders, you'd have to include terms like this. Okay, I'm now going to give an example of how we calculate stuff in the CFT. Maybe I'll pause for questions here and see if there are questions before we get into before we go further.
The reason there are no 1/c corrections to Gaussianities because all the states are at least order C. Is that aside from? Is that right? I mean, their energies are order C.
I mean, why is it non-perturbative? Yeah, I think that's right. I think that's right. Yeah. Okay. Any other questions at this point? Okay, so let me explain how I'm going to actually do a calculation. And a nice thing about this, so the CFT calculations that I'll describe and that we did in the paper, they're all easy. Okay, once you have the ensemble, it's easy to do these CFT calculations. The gravity calculations are hard. The CFT calculations are easy. I'm going to calculate for you now the averaged product of 4-point functions. We're going to do the whole calculation on one slide, basically. Okay, so we have this product of two 4-point functions. It's for the same 4 operators, but we allow them to be at different cross ratio. So x and x prime. The first step, expand in conformal blocks. I've just taken both of these 4-point functions and expanded them in conformal blocks. Since there's 2 of them, we have a double sum over conformal blocks. I've labeled the primaries by P and Q. Now we take this expression and average it over the ensemble. What does that mean? Well, first we just put a bar over these OP coefficients and use the definition of the ensemble. That's going to give you a delta PQ because the C12P and C12Q have to match up to give something non-zero. And it's going to give you some factors of this universal function C0. Then to do the sum is just going to become an integral against the Cardi density of states. Okay, that's it. That's the CFT calculation. So you get some C0s and you get some integral versus rho zeros of conformal blocks. This is a weird conformal block expansion now, because now because this delta PQ, we're now going to get a sum of conformal blocks of X times conformal blocks of X prime, where the weights are equal. So it's sort of a funny thing. We don't usually talk about in CFT that it's like a product of the same conformal block, but with different moduli. Now, what happens? So
why do you have a square in the previous equation on the conformal blocks? Am I missing something?
these are chiral conformal blocks. So each
okay.
correlator has a chiral block squared, chiral Virasoro blocks.
Okay, thanks.
Okay, so that's the answer. In this case, I'm now going to take C0 and plug in this formula that relates C0 to the DOZZ structure constants. What happens in this case is that when you do that, all of the rho zeros go away, and this just becomes a Liouville correlation function. So here's the formula. This is the answer for the average product of 4-point functions. On the left-hand side is like the actual CFT. Think of the left-hand side as the boundary CFT. This is the CFT that we're interested in. We're calculating the average in, and we're looking at this connected contribution. On the right-hand side, I've rewritten that average in terms of Liouville theory. It's an auxiliary. It's not like a real Liouville theory. It's just the answer you get. You can re-express in terms of these Liouville correlation functions. There are a few things to notice here. The most important one is that the cross ratios are mixed up on the right-hand side of this equation. So look closely. The left-hand side has XX bar and X bar prime. The right-hand side pairs the left movers with left movers in one Liouville and the right movers with right movers in the other Liouville. This is just how the average works, that these Liouville's are not like one for each CFT. They're like one for left movers and one for right movers. A funny thing about this is that even if the CFT calculation we're doing is Euclidean, the Liouville answer that we get can be effectively Lorentzian, because the arguments here are not complex conjugates. So they're branch cuts in this Liouville answer. That's going to match the fact that the particles can braid in Euclidean ADS. So this is going to match something on the gravity side. The next comment, the same formula applies to similar observables in 2 copies of the CFT at higher genus or with more insertions. That is, you can always write these 2 copy averages as Liouville observables. That's only true for 2 copies. More generally, say if you average GGG, the Cardi density of states factors do not cancel, and the answer is not a Liouville observable in general. This is sort of an accident that occurs in the case of two copy observables. As I mentioned before, at this order, all the CFT calculations are easy, like the one we just did, but the gravity calculations are involved. Now I'm going to turn to the gravity side, and I'll start, there are various solutions we can discuss. I'll start with the 2 boundary solutions of 3D gravity. These solutions were discussed by Maldacen and Maus. So here's an example. This is a 3-dimensional, this is a 3-manifold that solves the Einstein equations. What the picture means is that this manifold has the topology of a genus 2 surface times an interval. It has 2 asymptotic regions. So this is like one boundary, that's genus 2, and this over here is another separate boundary that's completely disconnected, and it's also genus 2. Each boundary has moduli associated to that Riemann surface. If the moduli are the same, then it's very easy to write down the metric. The metric is here. You can do this for any hyperbolic 2-manifold. You can just, given a hyperbolic 2-manifold, you can just stick it into this ansatz here, and you get a hyperbolic 3-manifold with the topology of 2-manifold times interval. These come from quotients of H3 by Fuchsian groups. So these we call Fuchsian wormholes. There are also solutions where the 2 boundaries here have different moduli. Those come from quotients by quasi-Fuchsian groups, so we call those quasi-Fuchsian wormholes. The simplest example of a wormhole like this is something that's related to the CFT 3-point function. Okay, so what's the simplest hyperbolic 2-manifold? It's the 3-punctured sphere. So that means that you can get a hyperbolic 3-manifold that looks like this. Let me explain this picture. This is in the usual dictionary of ADS CFT. This is something that would show up if you're trying to calculate the product of 3-point functions, because you just insert 3 operators on a sphere, that's the left, and you multiply that by 3 more operators on a sphere. But there's this connected topology that contributes. This is an on-shell solution of the Einstein equations, which has 3 particles back reacting on the geometry in order to support this wormhole solution. This solution exists only if the particles are heavy enough. So basically, that's what these equations are. This equation here is showing. Basically, these particles back react to produce conical deficits, and the total defect angle has to add up to more than 2 pi in order to get a solution like this. That's also another way of saying it, is that the conical defects have to be strong enough that you can put a hyperbolic metric on the 3-punctured sphere. Okay, so now we can calculate the on-shell action of this geometry. You have to renormalize the defects and be careful about all that sort of thing. So we calculated the on-shell action here, and what you find is C0 squared. C0, the universal formula for the 3-point functions. So this is the first hint that we're on the right track here, that there's a relationship between these wormholes. This is the relation, the basic identity that starts to relate the wormholes to the bootstrap. On the left, we have a gravity calculation of the action. On the right, we have this universal bootstrap function. Let's now look at something more elaborate.
Sorry, Tom, can I ask a question about the previous slide? So in the Diozzi paper, for example, they talk about a semi-classical limit of just the Diozzi formula, where they just compute an action on an S2 with the conical defects. Is your calculation closely related to that? Somehow the interval is not doing much, and like, just how is it working? Could you say a bit more about how the just the semi-classical limit of the DOZZ formula talked about in that paper relates to this calculation.
Yeah, it's very closely related because in order to calculate this gravity action, you first find a metric. You first find a hyperbolic metric on the three-punctured sphere,
Right.
and that's also how
Solving the
DOZZ
classical
calculated.
Liouville equation. Yeah.
Yes, exactly. Okay, so now they're not like literally the same because you have to also get these factors of rho zero to work out. But when you regulate everything carefully, that's exactly what happens.
I see. And somehow the rho direction is not playing that much of a role, is it? Or is the rho direction the integral over the rho direction? What is that doing?
In this calculation, it does basically nothing.
Okay.
The gravity calculation, in the case where you have equal moduli, the gravity calculation, really the rho direction basically just drops out, gives you a factor or something, and you end up with a boundary calculation that's a Liouville action, and that's why it can be related.
I see. Okay, thank you.
It's going to play an important role in this next one, though.
Okay, thanks.
So here's a more elaborate one. This is a wormhole that contributes to the 4-point function times 4-point function that we did the CFT calculation for a minute ago. So there are 4 particles now going through the wormhole. And now there's a modulus, the cross ratio. Okay, so there's some conformal cross ratio for the 4 points on the left boundary and a potentially different cross ratio for the 4 points on the right boundary. These kind of wormholes, in general, like higher genus, lots of defects, etc., can get extremely complicated. There is no general metric that you can write down for wormholes like this. However, if the moduli at the two ends are not too different in a precise sense that's been studied by mathematicians, then you can write the metric pretty explicitly. Here's the metric. Now, there's some complicated functions in this metric that I'm not going to tell you about, so it's a little more complicated than it looks. But you can write it down and study this metric. This is called the almost Fuchsian wormhole. This is a technical term that refers to this nearby, being nearby in moduli space of Uhlenbeck. Okay, so we calculated the gravitational action of these well, not just the almost Fuchsian ones, but also the other quasi-Fuchsian ones. I'm not going to go through that. We used some tricks from Teo and Taktajan, who also studied this action, and we extended it to include defects and used some of the results of Uhlenbeck. So we calculated this action, and we can calculate it for any of these wormholes. Here's an example where you have both higher genus and module and some operators inserted. So like this example here is something that would contribute to a 2-point function at genus 2 times another 2-point function at genus 2 with different insertion points and different moduli for the genus 2 surface on the two ends. At the end of the day, the answer that you get for this action is remarkably simple. If you have moduli lambda on the left and lambda prime on the right, then the gravitational action is turns out to be a sum of 2 Liouville actions. The Liouville actions are analytically continued to have these their arguments are not conjugate, so it's sort of like a Liouville action analytically continued to Lorentzian signature. This kind of structure you'll recognize from our CFT calculation, that the moduli, the cross ratios or moduli get mixed up on the two sides. Now, 3D gravity is not Liouville CFT, but the conclusion of this calculation is that 2 copies of the Liouville CFT does give you the semi-classical theory of 3D gravity on this fixed topology of interval times Riemann surface. So the punchline of this calculation is that this result agrees exactly with the large C CFT average. If we do this average calculation in the CFT, we also got product of Liouville stuff and the 2 things that agrees with our calculation on the gravity side.
Sorry, just like a question about the wormhole solution. I'm a bit confused. Like in flat space, I think the seminar wormhole is the Atlas wormhole, but there must be some ghost-like scanner to support the wormhole, and the energy condition is violated. Is this no seminar fields to support the wormhole?
No, this doesn't require anything funny, and there are no violations of any energy conditions.
Okay. Yeah. Thanks.
In fact, the one that you can do, you don't even need matter. Pure 3D gravity has solutions like this. If you want to add matter, you just add some massive particles and you find new solutions like this supported by the matter. They're really quite ordinary kind of solutions.
Yeah, I see. So there's no such simple generation to higher dimensions?
Well, I don't think we know. And in higher dimensions, there are theorems preventing this sort of thing if you have no sources at the boundary. And so that would be, so like, if I just gave you if I just said that the boundary was a sphere with no operator insertions, then you would have no wormholes like this. It was important to have the operator insertions. And I think there's a similar statement in higher dimensions that there's a no-go theorem without operator insertions. But I think once you have matter, there's no reason not to have this in higher dimensions as well.
Yep. Okay, thanks.
Sorry, Tom, I also have a question. So I'm trying to do a simple example. Let's take 4 points on the sphere and the square of that, like the CFD calculation that you described, with the same exact cross ratio on the 2 spheres.
Okay.
So then that one I could also do by the previous trick of computing the 4-point function on the sphere semi-classically in Liouville, like DOZZ could have done. You have more than 3 conical defects. So that would be more like just an interval times factorized times a 4-point function of the Liouville, right?
Yeah.
So how do the cross ratios get mixed up in that calculation? So if we had the exact same moduli on the 2 spheres.
They're not. So what happens is that the one you're describing would correspond to lambda prime equals lambda bar.
Oh, not lambda prime equals lambda.
Exactly.
Oh, I see.
There's an orientation reversal on the 2 sides.
Oh, I see. Okay, so then that's.
Then you just get a factor of 2.
Okay, thanks.
Okay, so the punchline was that this works for any of these quasi-Fuchsian 2-boundary wormholes, any genus with or without defects. We've also checked the 1-loop corrections, and they also match.
Sorry, Tom, I missed. Did you say your wormhole calculation matched the exact DOZZ formula or the semi-classical limit of the DOZZ?
Good. Semi-classical limit. So when I say that these agree, I mean the exponential in C part and the 1-loop prefactor. The DOZZ formula has non-perturbative corrections, of course. I have no idea if those have an interpretation on the gravity side. I think it would be really interesting to find them. Okay, so that was really the main evidence for this, and shows how these calculations work. But we've also done some other checks of the proposal. One is n-boundary wormholes. Okay, so by that I mean things like this. Okay, this is a 3-boundary wormhole. The CFT calculation for, say, GGG is easy. We've done that calculation. It's just like the one I showed you. The gravity calculation we haven't done. We've only done the gravity calculation by a trick where we analytically continue to the number of boundaries being 2 plus epsilon. So this is something that you can do if you assume that all the moduli are the same at the ends. And then you can use some tricks that were developed for the study of holographic entanglement entropy to do the gravity calculation at 2 plus epsilon, and it matches. Okay, so that's some evidence at least that these multi-boundary things also fit into this proposal. The other main check are handles. So by handles, I mean wormholes like this one or this one. So what I mean by handle is that we have just one boundary, but some non-trivial topology in the bulk. of that one boundary ADS. So we're in 3 dimensions. So this picture is how you make a handle. You cut out 2 spheres and you glue them together. So now you have like a shortcut through this sphere. This is a 3-dimensional analog of the picture on the right. So I'm just going to draw it this way, but we're in 3 dimensions. So all these pictures are really more like the one on the left. So these are very interesting solutions because they connect to some old work of Coleman and Giddings and Strominger. So let me spend my last few minutes talking about these handles. So back in the 80s, people were studying higher topology contributions to gravity. And Coleman, Giddings, and Strominger found this mechanism, or proposed this possibility, I should say, that when you include wormholes or higher topologies in the gravitational path integral, that this would lead to random bulk coupling constants. Now, the whole talk I've been discussing random stuff on the boundary side, but now I'm talking about something in the bulk. So what they said is that when you integrate out these wormholes, that would induce some non-local effective action. And you could interpret that by integrating in a random coupling constant in the bulk. We'll now see that this is exactly what happens in this model that we're talking about of 3D gravity plus point particles. There's an important difference that the wormholes here are on-shell classical solutions. In the Coleman story, they were mostly talking about like Planck-sized wormholes, and they were imagining that there was some mechanism to stabilize them, but didn't really have a concrete way of doing that. In this case, these are just classical. I'm just talking classical solutions. To illustrate this, I want to use the CFT ensemble to calculate the 4-point function of some of these particle operators. So say we're just purely CFT people doing a CFT calculation. Somebody handed us this CFT ensemble, and we want to calculate this 4-point function, 0101, 0202. Okay, so we write down the conformal block expansion. There's a contribution from the identity. The identity block for 1, 1 goes to identity, goes to 2, 2. This one is completely understood from the point of view of ADS CFT on the gravity side. It comes from so there's a relationship between the large C conformal blocks that show up on the CFT side and some gravity solutions with conical defects in them. So this term is understood as this geometry, and they match. But in the CFT ensemble that we discussed, there's also a contribution where you have a particle 3 running in the intermediate channel. You can't ignore this in the CFT ensemble because the C² 1, 2, 3, there's a wormhole for this. Okay, there's a wormhole that calculates C² 1, 2, 3. That was that 3-point, like 3 defect wormhole that I described a little while ago. So you can't set this OP coefficient to 0. This contribution is here in the CFT, and for this whole story to fit together, you need to understand what it means from the bulk. There has to be a match to the bulk, and there is. Okay, so there is a wormhole in the bulk, an on-shell solution that reproduces this term. Here's what the wormhole looks like. I forgot to fix my labels here. So this should, my 1s and 2s are mixed up a bit here. This should be 1, 1, and 2, 2. Okay, so this is a wormhole where you look at this it has the same boundary conditions as the 4-point function. These 4 operators are inserted, but there's a particle 3 running around the handle. And this is a saddle point of 3D gravity if the masses are large enough. And we can calculate the action of this saddle, and its action exactly reproduces this term here in the CFT ensemble calculation. So this wormhole had to be here for the story to make sense. And luckily we can go out and find it. We constructed the wormhole and calculated its action, and everything matches. So what about these random bulk coupling constants? Well, this on-shell wormhole contribution can be reinterpreted as a Witten diagram with a random coupling constant in the bulk Lagrangian. Okay, so the weird thing that's what this picture illustrates. We can either think of this as a wormhole, or we can think of it as a Witten diagram, where you sort of imagine like pinching the wormhole until it gets very, very, very tiny. It just becomes this dotted line. And these things are equal. So you can either use the wormhole or you can use the Witten diagram. But the vertices in this Witten diagram, there are now 3-point vertices here. And those 3-point vertices are random coupling constants in the bulk Lagrangian, which have the same statistics as the OP coefficients we were talking about in CFT. So a funny thing has happened here. We started with a bulk theory where there was no 3-point vertex in this bulk theory. They were not allowed, the 3 particles were not allowed to meet at a point. That was not something that we included at the beginning. But when once you include the wormhole, you get these 3-point vertices that are correlated by the randomness. There are similar wormholes, similar to this one, with nothing in the intermediate channel. So like if you calculate a 6-point function, 1, 2, 3, 4, 5, 6, there's a contribution to this 6-point function, which has an identity running in the intermediate channel, but again is correlated through disorder. And again, this is something that had to be there for this story to stick together, and you can find the saddle and everything works out nicely. Now there's another part of Coleman's story, which is the alpha states that came from. So he took these random bulk couplings and reinterpreted them as alpha states. If you suppose that what I'm telling you here is an exact statement about quantum gravity, then you would be led back into Coleman's story of alpha states. But I don't see that this is necessary, because I view what I'm doing here as an approximation or coarse graining. I don't think I'm describing here a UV complete theory of gravity. I'm describing some coarse grained observables. And in that case, I don't see a need for including the alpha states. Now, you could still ask, what do these wormholes I'm talking about here, what do they mean in a fixed UV complete theory? I don't know the answer, but I think a reasonable expectation is that these wormholes I've just told you about are quantifying the violation of global flavor symmetries by black holes. They're giving you a calculation of basically the rate of flavor symmetry violation. Because you can assign a flavor to each of these particles, and this is like some kind of amplitude squared for a black hole to spit out stuff with flavor. Okay, I'm gonna now wrap up. Summary is that higher topology solutions in 3D gravity correspond to average calculations in 2D CFT. We've checked many examples of this, but we don't have a systematic construction of all the topologies compared, for example, to topological recursion in JT gravity, where you really have an all orders comparison between calculations in the bulk and boundary. We don't have that. We don't have a systematic recursive definition, recursive procedure that gives a solution to all orders. I think it'd be interesting, very interesting to find that. There's the question, what does it all mean in a fixed theory? Which I told you I wasn't going to answer, and I'm not, but I think of it as some kind of coarse-grained description available to an IR observer. There are many things we've not addressed. I will just mention one of them, which is the sum over saddles. Okay, so the way I've described this is a saddle by saddle comparison. Okay, like there's a particular solution of 3D gravity, particular saddle in 3D gravity, and I've compared that to a particular term that you get when you do these averages in CFT. When you do the CFT average, there are various like contractions of the OP coefficients, and I've matched particular contractions of those OP coefficients to particular terms in the bulk. Now, presumably, you're supposed to sum over saddles. I haven't done that. This is really just a saddle by saddle analysis. A big complication there is that I think that if you're going to sum over saddles, which you probably should, you probably also have to include off-shell topologies. That is, contributions to the path integral that don't come from a saddle point or expanding around any saddle point. There's evidence from the torus partition function in the story of Maloney and Witten and follow-ups to that, that the off-shell contributions might be as big as the small corrections that you get when you sum over topologies. So that sounds difficult, but interesting. And I'll end there. Thank you.
All right, any questions for Tom? Marat?
Hi. I wanted to ask about this comment you made about the HPPS paper. Do you mean, do you have in mind something where if you try to do HPPS or whatever analogous thing, and you include, and you want to include black hole microstates, as you said, do you have in mind a scenario where you're sort of doing HPPS but with some averaging, and that should qualitatively change the answer? Or is there something else you had in mind? Do you have any more comments?
I don't have anything very specific in mind. All I meant to say was that, so there's HPPS in vacuum. There's your paper in the black hole, eternal black hole.
Mm-hmm.
But you could ask like, what is the grand picture here? You really want something like HPPS that applies for all expansions around all solutions, that includes in it somehow all of bulk effective theory. And the point I wanted to make is that it can't possibly just be that you solve the Bootstrap equations. That can't possibly be the answer, because the bulk has these non-factorizing contributions. So somehow the story has to really change once you start including not just the eternal black hole in the bulk, but like more complicated black hole contributions in the bulk, because then somehow you have to account for the non-factorizing terms. And I would say that we've only scratched the surface in terms of how you're supposed to understand the rest of bulk effective theory from the point of view of Bootstrap. But the crucial thing, or a crucial thing there being that you have to change the rules in some way in order to get these solutions.
Right. With the usual, I guess, with the underlying caveat that you don't want the UV complete density, you want to sort of look around the saddle and get some AR answer.
Right. If your goal is to reproduce the bulk effective theory,
right,
then you have to change the rules. Presumably, you keep the rules, keep the good rules if you want to reproduce the bulk string theory.
Right. Yeah. Thank you.
Tom, can I ask another question about sort of the averaging? I know you said you were not going to comment on the averaging, but from a technical perspective, I mean, if I were to kind of imagine something closer to having a family of theories, like for example, averaging over C, or maybe even something like a kinematic averaging where you average over the points of a correlator. I mean, is there any way to connect that kind of averaging? Because that to me seems fairly natural from a perspective of a low energy observer. Is there a connection between that and your prescription for averaging?
Not that we know of, I would say. I think we'd like to find that.
Okay.
But I don't really have anything else to say about it.
Thanks.
is a bit, I'll just add one thing. It's a bit like ETH in that, yeah, you could view ETH as an ensemble where you actually like do the random matrix integral or something, or you could view it as, you could ask what it tells you about an individual theory. And for the most part, that second thing is mostly answered by numerics. It's very hard to say much about individual theories.
Yui, do you have your hand up?
Yeah, it's me. Can I have a question? So I'm a bit confused about the wormhole contributions to the 4-point function of light operators. I mean, is that actually exponentially small at the LP limit where z goes to 0? Because the conformal block is something like z to the c, where c is the central charge.
The wormhole action is non-singular in the OP limit. So, well, it might have a power law singularity, but let's see. It certainly doesn't have a z to the minus c type term. It might have a order 1 type singularity, but it is much weaker singularity than you get in the actual 4-point function. The singularities in the wormhole, well, basically, you know, you're now joined to your partner across the wormhole. You're not joined to the one that's nearby. So the singularities are much softer. Did that answer your question?
Yeah. So is that, I mean, any particular reason that you don't consider the 1/c correction to the identity block? Sorry, to the identity extreme.
I'm not sure you mean. We did include the 1/c corrections to this, and those also matched.
Okay.
Yeah.
Sorry. Thanks.
Tom, is there any prospects for a gravity proof, like a recursive proof, so that, you know, it seems like you guys are checking it every time and matching, but any prospects for that?
I would love to do that, but I don't know. We don't have it.
Yeah.
I think okay, I don't know. I'm an optimist. I think it probably can be done. But I don't have a proposal.
Fair enough.
So Tom, I think I don't understand why this speculation, you say that is coarse grain description is just a speculation. Isn't that literally what you're doing? You're averaging over, you're kind of doing a microcanonical window, which is what I guess when yeah, you're right. No, there's a vague sense in which it's not a speculation. That's what this is. It's a coarse grain description. I guess when I say it's a speculation, what I mean is that we don't know what that coarse graining is. It's not that I can say, here's a calculation in a fixed theory that has the following coarse graining because of my experiment, has the following resolution, and the answer I get agrees with the wormholes. I think that's what we would like, is some kind of words along those lines. But we don't have that. So that's all I meant. And even if you take ETH as a given, you still don't have it? In the sense that the ETH says something about, you know, measurements, coarse grain measurements you might actually make.
Well, again, I think you have it in a vague sense, but I'm not sure that I'm not sure what the precise statement is. I'm not sure what I'm not sure what equation I can write in a fixed theory where I like understand all the errors. I would like to have like an equation in a fixed theory where I understand what the corrections are and this is the leading term. Even for ETH, I'm not exactly sure what, even if I assume ETH, maybe if you assume ETH, you could do something like that.
Murat, is your hand still, is it up again or is that from before? I guess it was from before.
Sorry, that was from before. I never logged
Uh,
in. Sorry.
Any other questions for Tom? All right. Well, thanks again for a great talk and ciao.